Hello! Welcome to today's lesson on transformers. We'll begin today's lesson by looking at how a transformer transfers energy between two circuits using electromagnetic induction. Next, we'll discuss the components of a simple transformer. Finally, we will review how transformers function, highlighting the role of alternating current in the induction process. So far, we have explored the fundamentals of magnetism and electromagnetism, including magnetic fields and how they interact with electric currents. We have also discussed electromagnetic induction, where a changing magnetic field can induce an electric current in a coil of wire. Building on this foundation, we can now delve into transformers. This lesson will deepen our understanding of how we manipulate electrical energy, which is crucial for numerous applications like power distribution and electronic devices. Let's get started.
So, what is a transformer?
A transformer is an electrical device designed to transfer electrical energy between two or more circuits through the process of electromagnetic induction. It primarily functions to change the voltage of an alternating current, AC, making it higher, stepping up, or lower, stepping down, depending on the requirement. A basic transformer consists of two main components: the primary coil, which is the coil that receives the initial electrical energy from an AC source. The secondary coil, which is the coil that delivers the electric energy at a different voltage to the output circuit. Both coils are wound around a shared core, usually made of iron. The iron core is an essential part of a transformer because it can be easily magnetized. When an alternating current flows through the primary coil, it creates a magnetic field that magnetizes the iron core. This magnetization helps focus the magnetic field between the primary and secondary coils. By using an iron core, the transformer reduces energy loss during the transfer of electrical energy. More of the magnetic field generated by the primary coil is linked to the secondary coil, which allows for a more efficient transfer of voltage. Transformers operate only with alternating current. When this current flows through the primary coil, it generates an alternating magnetic field around the coil. This magnetic field then propagates through the iron core, which in turn magnetizes the core. The alternating magnetic field in the iron core induces an alternating voltage in the secondary coil. This process is known as electromagnetic induction. Let's go through some points that are important to note. Depending on the design, the induced voltage in the secondary coil can be higher or lower than that in the primary coil. We will explore this in detail in future lessons. One essential property to remember is that the frequency of the voltage induced in the secondary coil will be the same as the frequency of the AC supplied to the primary coil. This is crucial for ensuring compatibility with different electrical devices. Finally, for the induced voltage in the secondary coil to result in an actual flow of electric current, the secondary coil must be part of a complete circuit. If it is, an alternating current AC will flow through it, delivering power at the adjusted voltage. That completes our introduction to transformers. To summarize, in today's lesson, we delved into the fundamentals of transformers, focusing on their role in transferring electrical energy between circuits via electromagnetic induction. We explored the basic structure of transformers, which includes primary and secondary coils wound around an iron core, and understood the importance of the iron core in efficiently channeling the magnetic field. We discussed how transformers operate exclusively with alternating current, as this generates an alternating magnetic field necessary for induction in the secondary coil. We also highlighted that the induced voltage frequency in the secondary coil remains consistent with the primary AC's frequency. Additionally, we noted that for the induced current to flow, the secondary coil must be part of a complete circuit. These principles are crucial for practical applications such as power distribution and electronic devices. In future lessons, we will examine how the design of a transformer affects voltage changes and delve into specific calculations related to transformers. Watch the rest of the GCSE physics course at Sophos Education.